So now let's take a look at what's called inverse variation. So inverse variation, when one quantity increases as the other decreases, an inverse variation arises. In other words, examples of constant variations is like as one variable increases, so does the other one, or as one decreases, so does the other one, right? So the graph is very linear and they go in the exact same direction. That's direct variation. Inverse variation is the inverse of that, right? So direct variation is y equals k times x, where k and x are being multiplied. Well, what's the inverse of multiplication? Well, that would be division. So our inverse variation function is y equals k divided by x. That's inverse variation, right? Because that's division is the inverse of multiplication. So I wanted to show you an example of what inverse variation would look like on a table. So inverse variation on a table would be how the speed and time compare here. As my speed is increasing, my time is decreasing. And so this is an example of inverse variation, because as one of my variables is going up, the other variable is going down or getting smaller. So let's take a look at example 3. We're given that y varies inversely as x, meaning we're dealing with an inverse variation setup. So in other words, y equals k divided by x. And we can use the exact same process we did in the first two examples to write an inverse variation function here for this setup. So we're told that y equals 4 when x is equal to 5. So we can plug those values in. So 4 equals k divided by 5. Solving for k, we'd multiply both sides by 5, and we would get 20 is equal to k. And again, that's multiplying both sides by 5, oops, there we go, to solve for k. So we have just figured out then that our equation would be y equals 20 over x. This is our inverse variation function, our inverse variation equation. And we have to graph this one. Now, graphing this one is not as easy as it was with direct variation because this is not a linear equation anymore. So this is going to take a little bit more work. So I am actually going to move my video up here. And what we're going to do is we're going to end up creating a table for this. So let me use a different color. I'm going to create a table. You could use a graphing calculator or something like that as well, but I just want to show you what it looks like using the table. So I'm going to pick some values that are negative and some that are positive, and I'm going to plug them in for x. So using numbers like maybe, and knowing that our x's are going to be divided into 20. So I'm going to use a number like maybe -5 and -4 and -2 and 0 and +2, +4, and +5. And let's see what happens when we divide these values. So again, these values of x that I've chosen are going to be divided into 20. So 20 divided by -5 is a value of -4. 20 divided by -4 is -5. 20 divided by -2 is -10. 20 divided by 0, don't be tricked by this, it's undefined, meaning it does not exist because we can't divide by 0. So what that ends up doing is it creates this asymptote that divides our graph in half, and it's going to create what looks like two graphs, but is really one. And the reason why it's going to look like that is because we are not allowed to divide by 0. Okay, and this will make a little bit more sense once you see the picture this graph gives us. Now, 20 divided by +2 is +10, divided by 4 is 5, and divided by 5 is 4. So I chose these numbers because I knew I was going to be dividing them into 20, so I picked numbers that were easy to divide. If you chose numbers like -3, -2, -1, that would have been just as fine. I just chose numbers that I knew were going to divide nicely. So let's graph as many of these points as we can. So we have the point -5, -4. Then we have the point -4, -5. And then we have the point -2, -10, which is kind of off our graph, but if I do it like here, you can kind of see it. 0 is undefined. Now we have the positive numbers. 2 positive 10, 4 positive 5, and 5 positive 4. Notice how this really doesn't look like much of anything, and these points are in opposite quadrants, right? And so this is looking pretty weird with what we have drawn so far with these points. So I'm going to fill in what this actually looks like. Oops. And we did talk about these way at the beginning of the school year, and it's been some time. Oops. I'm trying to draw an arrow on the bottom of this, but the iPad does not like it. Okay, there we go. So this is what this graph looks like, these inverse variation functions, where it looks like we have two separate graphs curved, kind of going in those opposite directions. It's almost like I could draw a line, a diagonal line through this, right? Like right in here somewhere. And if I folded this on top of one another, these two curves would match up. So they almost look like a reflection of one another, right? But together, these two curved pieces together make the graph of this one equation, y equals 20 divided by x. And you're going to notice that this entire unit 5, is all about functions and equations that look like this, where x is in the denominator, and we end up getting these two curved pieces that really together make one function. Oops, here we go. All right, so that finishes up 5.1. So this is kind of a shorter lesson. So we talked about direct variation functions where y varies directly as x, and that's where you have your constant of variation k being multiplied by x. And then we talked about inverse variation functions, which is where you're using the inverse operation of that, where we're dividing by x. So you're now good to work on the 5.1 worksheet. Please let myself or Mr. Brasser know if you have any questions. Have an awesome day, guys. Bye.